And now in this lecture we'll find out the area of square ABCD. In the moment we have square ABCD. We know that DB is the diagonal of this square ABCD. This is angle BDP, that is equals to 30 degrees in its size. This is angle PBC, that is also equal to 30 degrees in its size. Line segment PB equals to 5 units in its length. Again, our test is to find out the area of this square ABCD. So, first of all, we know that DB is the diagonal of this square. Therefore, it bisects those two angles into two halves. One angle of this square is 90 degrees, and therefore it bisects the angles of square ABCD into two halves. Each half must be equal to 45 degrees in its size. So this is the first half, that equals to 45 degrees in its side. And this is the second half, that must be equal to 45 degrees in its size. But this angle equals to 30 degrees, and therefore this missing angle must be equal to 15 degrees in its size, because 15 plus 30 is 45. Likewise, the diagonal DB bisects angle ABC. So the size of this angle is 45 degrees. So this missing angle must be equal to 15 degrees in its size, while y equals 15 plus 30 degrees is 45 degrees. This is one half of angle ABC. So this angle must be equal to 15 degrees in its size. And this angle must be also equal to 45 degrees in its size, because the diagonal DB bisects angle ABC. So this angle must be equal to 45 degrees in its size. So in the next step we will do a construction, that is to say, from point C, from this point C, we will draw angle bisector of angle DCB. Again, from point C, we will construct angle bisector of angle DCB. We find this point as point Q. So CQ is angle bisector of angle DCB. Therefore, this angle must be equal to 45 degrees in its size, and this angle must be also equal to 45 degrees in its size. CQ bisects, the bisector CQ bisects angle DCB into two halves. Each half must be equal to 45 degrees in its size. In the next step, we will extend line segment DP until it touches the angle bisector. So the extended side DP touches angle bisector CQ at point Q. So this is triangle DQC, the triangle DQC this angle equals to 45 degrees. This angle equals to 15 degrees. 45 degrees plus 15 degrees is 60 degrees. And therefore this third angle must be equal to 120 degrees in its size. According to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So this missing angle, this third missing angle must be equal to 120 degrees in its size. The next step, we join points B and Q together by a straight line. We join points B and Q, create a triangle BQC. This is triangle BQC. So, in the next step, we prove that triangle BQC, this is triangle BQC, that it is congruent to this triangle BUD. We prove that those two triangles can go into each other according to side angle side rule. So why those two triangles can go into each other? We prove that triangle BQC, this is triangle BQC. It is congruent to this triangle DQC. So, why those two triangles can go into each other? First of all, side DC of this triangle DCQ is equal to side BC of this triangle BQC. Again, those two sides are equal to each other because of the fact that we know that all the sides of any square are equal to each other. So side DC of this triangle DCQ is equal to this side BC of triangle BCQ. So both the two sides of square ABCD and therefore they are equal to each other. In the end, I should hold on that side BC of triangle CQ is equal to side BC of this triangle BQC. They are both the sides of the square ABCD and therefore they are equal to each other. In addition, those two angles are both equal to 45 degrees and therefore they are equal to each other. So since this is angle DCQ, and it is equal to this angle BCQ. Again, I should hold that angle BCQ in triangle BCQ is equal to angle DCQ in triangle DQC. They are both equal to 45 degrees and therefore they are equal to each other. And finally, this is side QC. It is a common side and it belongs to both triangles. So QC equals to itself as a common side that belongs to both triangles. And again, side QC is a common side that belongs to both triangles, so I can write down that QC equals to itself. It's a common side that belongs to both triangles. So if we prove that those two sides and the angle that is included between those two sides in this triangle DQC are correspondingly equal to those two sides, and the angle that is included between those two sides in this triangle QCB. And therefore, those two triangles can point to each other according to side angle side rule. So if you know that triangle BQC can point to triangle DQC according to side angle side rule. If those two sides and the angle that is included between those two sides in triangle DCQ are correspondingly equal to those two sides and the angle that is included between those two sides in triangle BQC, and therefore those two triangles can point to each other according to side angle side rule. And from the fact that those two triangles can point to each other, we derive that those two angles are also equal to each other according to the rule that corresponding angles can point triangles are equal to each other. Those two triangles can point to each other, and therefore those two corresponding angles must be also equal to each other in their sizes. So therefore this is angle CDQ. And it is equal to this angle, that is angle QBC, the triangle QBC. Again, from the fact that those two triangles can point to each other, we derive that angle CDQ, the triangle DQC is equal to angle QBC, triangle BQC. But angle CDQ equals to 15 degrees in its side, so I can write that angle CDQ equals to 15 degrees. And for this equation, we derive that angle QBC also equal to 15 degrees in its size. This is angle QBC is equal to 15 degrees in its size. In the next step, we will prove that those two triangles can point to each other according to angle side angle rule. Okay, again we prove that this is triangle BQC and this can point to this triangle BQP according to angle side angle rule. So while those two triangles can point to each other, we have to prove that those two triangles can point to each other according to angle side angle rule. So we have to prove that triangle BQC, this is triangle BQC, and this can point to this triangle PBQ according to angle side angle rule. But before that, this triangle BQC this angle equals to 45 degrees, this angle equals to 15 degrees, and therefore 45 degrees plus 15 degrees is 60 degrees, and therefore this first missing angle must be equal to 120 degrees in its size. We know that the sum of the angles around any point is equal to 360 degrees. Again, the sum of the angles around any point is equal to 360 degrees. And therefore, the sum of the angles around this point Q must be equal to 360 degrees. So which angles we have around point Q? We have 120 degrees plus 120 degrees is 240 degrees, and therefore this first missing angle must be equal to 120 degrees in its size. So 120 degrees times 3 is 360 degrees. The next step, we'll copy triangle BDP in a new page, and we'll implement rule 2 that talks about the size of angle of an external angle of a triangle. We'll implement rule 8 on triangle BDP. This is triangle BDP, is equal to the original drawing. This triangle BDP, those three angles are defined as an external angle. Angle BQ, angle BPQ. This is angle BPQ. This is an external angle for this triangle BQP. Triangle BDP. This is triangle BDP, and angle BPQ. This angle is defined as an external angle of triangle BDP. So I paid rule 8, and we implement rule 8 on triangle BDP. This triangle BDP. Only for rule 8. The external angle of a triangle is equal to the sum of the two interangles that are not adjacent to it. This is triangle ABC. those are angles alpha, beta, and gamma that are defined as symmetric angles. This is angle E that is defined as triangle from triangle ABC because of the fact that it is located outside triangle ABC. According to this rule 8, the size of this angle E it is equal to the sum of the two triangles that are not adjacent to it. This is angle gamma that is definitely adjacent to angle E. The two other angles that are not adjacent to it are those two angles alpha and beta. So according to this rule 8, the size of this angle E must be equal to the sum of the two angles that are not adjacent to it. Those are the two angles that are not adjacent to it, and the sum of those two angles is equal to alpha plus beta. So the angle E is equal to alpha plus beta. E equals to alpha plus beta. So we can implement rule 8 in our drawing. Because in our drawing we have the rectangle BPQ. The rectangle BPQ according to rule 8 must be equal to the sum of the two angles that are not adjacent to it. This angle is definitely adjacent to angle BPQ. Those are the two angles that are not adjacent to it. And therefore, the size of angle BPQ must be equal to the sum of those two angles that are not adjacent to it. That is to say, it must be equal to 15 degrees plus 30 degrees. So, the angle BPQ must be equal to the sum of those two angles, that is 15 degrees plus 30 degrees is 45 degrees. So the angle BPQ is equal to 45 degrees in size according to rule 8. This is the angle BPQ is equal to 45 degrees in its size. In the next step, we prove that those two triangles can go into each other according to angle sine angle rule. That is to say, we prove that triangle BQC, this is triangle BQC, can go into this triangle BPQ according to angle sine angle rule. So we have to prove that triangle BCQ can go into this triangle BPQ according to angle sine angle rule. So why those two triangles can go into each other? First of all, we know that this angle equals to 30 degrees, and therefore this missing angle must be equal to 15 degrees in its size. Why? Because 15 plus 15 is 30. You can say, you can see it in another way, that DB bisect angle ABC. Again, DB, the diagonal DB bisect angle ABC. So this angle equals to 45 degrees, and this angle must also equal to 45 degrees in size. So 15 degrees plus 15 degrees plus the missing angle, in total must be equal to 45 degrees, and therefore this missing angle must be equal to 15 degrees in size, because 15 times 3 is 45. Each half is 45 degrees. So this one is 45 degrees, and therefore the second half must be also equal to 45 degrees in size, and therefore this missing angle must be equal to 15 degrees in its size. So actually, those two angles are both equal to 15 degrees, and therefore they are equal to each other. So here this is angle QBC. A triangle QBC, and it is equal to this angle. It's actually angle PBQ. A triangle PBQ. And again, angle QBC triangle BCQ equals to angle PBQ triangle BPQ. They are both equal to 15 degrees and therefore they are equal to each other. In addition, PB QC, this is side QB. This is a common side that belongs to both triangles. QB belongs to triangle PBQ, and QB also belongs to triangle QBC. So QB equals to itself. It's a common side that belongs to both triangles. Again, QB equals, side QB equals to itself. It's a common side that belongs to both triangles. And finally, those two angles are both equal to 45 degrees and therefore they are equal to each other. So here this is again QCB. The triangle BQC. And it is equal to this angle, the angle BPQ. The triangle PBQ. And again, I should know that angle BCQ and triangle BCQ is equal to angle BPQ and triangle BPQ. They are both equal to 45 degrees and therefore they are equal to each other. So, we actually found out that those two we have also those two angles. They are both equal to 180 degrees in their sizes and therefore they are equal to each other. So actually this is angle PQ, this is angle CQB, and triangle BCQ. And this is equal to this angle, this is actually angle PQB. In triangle PBQ. They are both equal to 120 degrees in their sizes and therefore they are equal to each other. And again, angle CQB, triangle BCQ equals to angle PQB, triangle BPQ. They are both equal to 120 degrees in their sizes and therefore they are equal to each other. So actually found out that those two angles and the side that is included between those two angles, that is side QB, are correspondingly equal to those two angles. So those two angles and the side that is included between those two angles in triangle BCQ are correspondingly equal to those two angles, and the side that is included between those two angles in triangle PBQ. And therefore those two triangles can go into each other according to angle, side, angle rule. We have those two angles and the side that is included between those two angles in triangle BCQ are correspondingly equal to those two angles and the side that is included between those two angles in triangle PQB. And therefore those two triangles can go into each other according to angle, side, angle rule. So now we should find out that triangle BCQ can write, this is the same can write to triangle BPQ according to angle side angle rule. And from the fact that those two triangles can go into each other, we derive that side PB, this triangle PQB, is equal to this side BC, the triangle BCQ. Those two sides, the corresponding side BC is the corresponding side of side BP. Why? BC is the corresponding side of side BP because of the fact that BC is located in front of this angle is equals to 120 degrees, and likewise BP also located in front of those two angles is equal to 120 degrees in size, and therefore those two sides are corresponding sides. So those two corresponding sides are equal to each other according to all the corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding sides must be also equal to each other and their lengths. So, if you found out that according to the rule I mentioned, BC is equal to BP, or PB is equal to BC, but PB equals to 5 units in its length according to what is the equation. And for this equation, 5 equals to PB equals to BC, we derive that side BC is also equal to 5 units in its length. Here, side BC is equal to 5 units in its length. Our test is to find out the area of this square ABCD. So, what is the area of square ABCD? Actually, we know that the area of any square equals to the length of one side squared. It is equal to the length of one side squared, and therefore the area of square ABCD must be equal to the length of BC squared. So the area of square ABCD equals to the length of side BC squared, that is actually the area of any square. The length of one side squared. BC is 5, therefore BC square is 5 square, that is 25. So in total we found out that the area that we are looking for in this question, that is the area of square ABCD, is equal to 25 square units in its size. So we finish the rest of the question. In the next step, I'll start the lecture. This lecture, our test is to find out the area of this square ABCD. So in the moment we have square ABCD, DB is the diagonal of this square ABCD. We know that BP equals to 5 units in its length, and this is again DP is equal to 30 degrees in size. This is again CBP is also equal to 30 degrees in size. Again, our test is to find out the area of this square ABCD. So first of all, we know that the diagonal of any square bisects the angles of the square. So the diagonal DB, this is diagonal BD, it bisects those two angles of the square. You know that all the angles of any square are right angles. So this is diagonal DB, it bisects angle ABC. ABC in total is 90 degrees, so the first half is 45 degrees, and the second half is also 45 degrees. But this angle equals to 30 degrees, and therefore this missing angle must be equal to 15 degrees in size, because 15 plus 30 is 45 degrees. Likewise, the diagonal BD bisect angle ADC. So the first half is 45 degrees, and the second half, this is the second half, is also 45 degrees. So 30 degrees plus the missing angle total must be equal to 45 degrees, and therefore this missing angle must be equal to 15 degrees in its size. In the next step, we did the construction. That is to say, from point C, we go angle bisector of angle DCB. Again, from point C, we go angle bisector of angle DCB. So first of all, CQ is angle bisector, and therefore this angle equals to 45 degrees, and this angle also equals to 45 degrees. In the next step, we extended side DP until it touches the angle bisector. Touches the angle bisector of point Q. This way, triangle DQC. Triangle DQC, this angle equals to 45 degrees, this angle equals to 15 degrees, 45 degrees plus 15 degrees is 60 degrees, and therefore this third angle was equal to 120 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. And the next step, we actually prove that those two triangles can go into each other according to side against side rule. So why those two triangles can go into each other? First of all, those two sides are both the sides of the square, therefore they are equal to each other, because we know that all the sides of any square are equal to each other. In addition, those two angles are both equal to 45 degrees, and therefore they are equal to each other. And finally, QC is the common side that belongs to both triangles. So if you prove that those two sides and the angle that is included between those two sides, the triangle DQC are correspondingly equal to those two sides, and the angle that is included between those two sides is triangle QCB, and therefore those two triangles can go into each other according to side angle side rule. So again, if you found that triangle BCQ can go in, this is the side of can go to triangle DQC according to side angle side rule. And for the fact that those two triangles can go into each other, we derive that those two angles must be also equal to each other in their sides. According to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other in their lengths. So angle QDC is equal to this angle QBC. And again, angle CDQ equals to angle QBC. But this is angle CDQ that equals to 15 degrees. So you can write down here that angle CDQ equals to 15, and from this equation 15 equals to angle CDQ equals to angle QBC, we derive that angle QBC must be also equal to 15 degrees in its side. This is angle QBC that equals to 15 degrees in its size. Roughly, this triangle BQC, this angle equals to 15 degrees, this angle equals to 45 degrees, 15 degrees plus 45 degrees is 60 degrees, and therefore this final angle must be equal to 120 degrees in its size. We also know that the sum of the angles around any point is equal to 360 degrees. So 120 degrees plus 120 degrees is 240 degrees, and therefore this missing angle must be equal to 120 degrees in its size, because the sum of the angles around point Q must be equal to 360 degrees according to the rule dimension. Therefore, this missing angle must be equal to 120 degrees in its size. In the next step, we prove that those two triangles can go into each other according to angle side angle rule, but before that, I copy triangle DPB, this triangle, and in your page we implemented angle 8 that talks about the size of the external angle of a triangle in this drawing. In triangle DBP. This is a triangle DBP. Okay, this is a triangle BDP or DBP. This is a comment from the original drawing. According to Rule 8, an external angle of a triangle is equal to the sum of the two triangles that are not adjacent to it. This is the external angle BPQ. It is equal to the sum of those two triangles that are not adjacent to it. That is to say, it must be equal to 13 degrees plus 15 degrees, that is 45 degrees. So this is the missing angle BPQ. It is equal to 45 degrees in its size. Angle BPQ equals to 45 degrees in size. This is angle BPQ is equals to 45 degrees in size. Here we have this angle, diagonal DB bisect angle ABC. So this the first half is 45 degrees, and the second half is also 45 degrees because DB bisect angle ABC. So the second half is also 45 degrees. So 15 degrees plus 15 degrees is 30 degrees, and therefore this missing side must be equal to 15 degrees in size. So in the next step, we prove that those two triangles can join to each other according to angle, side, angle rule. That is to say, we prove that triangle BQC, this is triangle BQC, can join to this triangle PQB according to angle, side, angle rule. So why those two triangles can join to each other? First of all, angle QBC equals to angle PBQ. Angle QBC, that is 50 degrees, equals to angle PBQ. Angle PBQ. They are both equal to 15 degrees and therefore they are equal to each other. In addition, QB is a common side that belongs to both triangles, so we can write down that QB equals to itself as a common side that belongs to both triangles. And finally, those two angles are both equal to 45 degrees and therefore they are equal to each other. So we should find out that but before that, so we actually found out that this angle equals to 120 degrees according to what we already found out. So we found out this angle also equals to 120 degrees. So we found out that those two angles and the side that is included between those two angles in triangle BQC are corresponding equal to those two angles, and the side that is included between those two angles in triangle PBQ. And therefore those two triangles can join to each other according to angle, side, angle rule. We have those two angles and the side that is included between those two angles, that is side QB, in triangle BQC, that corresponding equal to those two angles, and the side that is included between those two angles, that is side BQ, in triangle BQP, and therefore those two triangles can join to each other according to angle, side, angle rule. Which again, if you follow that triangle BCQ can join, this is the side can join to triangle BPQ according to angle, side, angle rule. And from the fact that those two triangles can join to each other, we derive that side BC is equal to side BP again. We derive that those two sides are equal to each other according to the rule that corresponding sides in one triangles are equal to each other. Those two triangles can join to each other, and therefore those two corresponding sides are also equal to each other in the ellipse. Those are corresponding sides because of the fact that BC is located in front of angle equals to 120 degrees. Likewise, PB is also located in front of those triangles that is equal to 120 degrees in size. And therefore, those are the two corresponding sides that are located in those two inside those two one triangles, and therefore must be equal to each other in their length. So BC equals to PB. Therefore, that BC equals to PB. But according to what is given in the question, PB is 5. So we can write here that PB is 5. From the question, we have that BC 5 equals to BP equals to DC. From this equation, we derive that BC equals to 5. Okay, BC equals to 5. So if we know that BC equals to 5, our task is to find out the square ABCD. We know that the n square equals to the length of one side squared. So thereafter ABCD must be equal to the length of side BC squared. BC is 5, therefore BC squared is 5 squared, that is 25. So total if you know that they have this square that is there that we're looking for, they have this square ABCD is equal to 25 squared in size. Okay, thank you very much.